Yes, thanks for the introduction. So this is joint work with Martin Ekra, where we have extended Regev's recently introduced quantum factoring algorithm to also allow it to be used to compute discrete logarithms. And the integer factoring problem and the discrete logarithm problem have, at least historically, been the basis for essentially all widely deployed asymmetric cryptography. And these two problems are not directly related to each other, but there has still been the case that an algorithm that have been developed for either of these problems have often been possible to adapt to solve the other of these problems. This has especially been the case for this for Shor's algorithm, where a slight variation of the algorithm can be used to solve both of these problems. And the cost of Shor's algorithm in terms of the circuit size required to implement the algorithm is essentially determined by the number of modular multiplications that must be performed by the circuit. And Shor's algorithm is actually very efficient, requiring only on the order of n such modular multiplications to solve an n-bit problem instance. And it was therefore quite surprising when Regev last year introduced a new quantum factoring algorithm with an asymptotic advantage in the per run cost compared to Shor's algorithm. And Regev's algorithm can be seen as a multidimensional analog to Shor's algorithm and can factor an integer with a circuit that only has to perform on the order of square root of n modular multiplications per run. Now this comes with the downside of the circuit having to be repeated multiple times and of the circuit having to use asymptotically more memory than Shor's algorithm. This was later somewhat rectified by Regev and Ketanatan, who managed to decrease the space usage of the algorithm to be within a constant factor to that of Shor's original quantum factoring algorithm. And the circuit did, however, still have to be repeated on the order of square root of n times in order to actually factor the target integer. And the overall cost of the algorithm is therefore on par with asymptotically on par with Shor's algorithm. But this per run, this advantage in the per run cost is still very interesting, as it seems like an easier task to build a smaller quantum computer and using this to run a smaller circuit multiple times than it is to build a larger quantum computer and using it to run a larger circuit a single time. And the Regev's algorithm and the space-saving optimizations of Regev and Ketanatan did, however, only consider the integer factoring problem. And this is where our work come in, as we have extended the algorithm to also be used to solve the discrete logarithm problem. And our extension can also make use of the space-saving optimizations of Regev and Ketanatan, meaning that we have the same asymptotic advantage over Shor's discrete logarithm algorithm as Regev's algorithm has over the Shor's factoring algorithm. And the high-level idea behind all of these quantum circuits, so both Shor's and Regev's algorithm, is actually quite similar, implemented by a similar circuit, with the primary difference being in the number of these initial control registers. For Shor's algorithm, only a single such control register is used, whereas for Regev's algorithm, a larger number, D, is used with a primary focus of D equal to square root of n. For both algorithms, the control registers are initialized to some initial state. Some basis elements are then exponentiated into another register, conditioned on the values of these control registers. After this, a quantum Fourier transform is performed over the control registers, and the control registers are then measured, with the measured results being the output of the quantum algorithm. And for Regev to actually achieve an asymptotic per run advantage over Shor's algorithm, he also has to perform a slight trick in order to improve the efficiency. And this trick is to reorder the multiplications and ensure that the basis elements are small integers. By doing this, he ensures that small integers are multiplied with other small integers, and the product of two small integers can be computed quite efficiently and results in another quite small integer. So this means that the full product of up to D small integers can be computed with a cost that is negligible compared to the cost of a single modular multiplication And by doing this, he can essentially increase the value of D without increasing the cost of the circuit if he keeps the initial state the same. And the actual performance gain he achieves is due to the fact that a larger value for D, so more control registers, allows a smaller initial state to be used while still achieving useful quantum interference. And the high-level purpose of these algorithms, both Shor's and Regev's, is also quite similar in that they are used to find the periodicity of a function. Now, for Shor's algorithm, the quantum part of this algorithm is used to find the periodicity of a one variable function. So in this example, for example, you can see that it finds periodicity of this function, which is around 300, with the pattern repeating after this. Meanwhile, for Regev's algorithm, he considers a D variable function defined like this. And as you can see, this two-dimensional example, it forms a pattern that repeats in two different directions. And this periodic pattern forms a lattice. And so in this case, a two-dimensional lattice. But in the general case, it forms a D-dimensional lattice, which you can define like this. And each run of Regev's quantum circuit provides some information about this lattice. To actually factor the target integer, Regev also relies upon a heuristic assumption, under which he can argue that given essentially D runs of the quantum algorithm, or output from D runs, he can jointly post-process these and factor the target integer. And with this background out of the way, I will continue with our extension of the algorithm to compute discrete logarithms. And as with Regev's algorithm, we consider a function and use a quantum algorithm to analyze the periodicity of this function, with our function being quite similar to the one considered by Regev, but with an additional dependence on a specific discrete logarithm problem instance. This also impacts how the quantum circuit looks, with the function having to be computed on the final register based on the control registers. And this poses a minor issue, since Regev, the efficiency of his algorithm, crucially relies on the fact that all the A1 to AD are small integers, but we are not guaranteed that X and G, which are a discrete logarithm instance, are small. But this is only a minor issue because we only have to raise X and G to quite small exponents, and the asymptotic cost of the circuit is therefore still on the order of square root of n modular multiplications. And as with Regev's algorithm, each run of our quantum circuit gives some information about the lattice, which in our case is defined like this, which that has a dependence on the discrete logarithm problem instance. And we make a new heuristic assumption under which we can argue that jointly post-processing, essentially the output of essentially D runs of the quantum algorithm, allows us to actually recover a basis for this lattice. And it's quite easily seen that this vector here, which directly provides us the solution to the discrete logarithm problem instance, is a part of this lattice. And it's also quite easy to recover this vector if we have a basis for the lattice, allowing us to solve the discrete logarithm problem instance. And as I said, our analysis relies upon a new heuristic assumption. And this new heuristic assumption is actually somewhat stronger than the heuristic assumption that made by Regev. But both of our assumptions essentially correspond to assuming that small primes behaves as random elements in a multiplicative groups of integers. And to actually prove this seems like a quite hard task. But interestingly, Pilat here at Oxford recently managed to prove a variant of our assumption. And relying on this proven variant of our assumption would require using significantly larger parameters for the quantum algorithm than we believe to be necessary, but it still provides the same asymptotic advantage over Shor's algorithm. So this is very interesting, giving an algorithm which does not rely on any heuristic assumption. Our new stronger heuristic assumption also allows us to quite easily develop further variants of Regev's algorithm. For instance, a variant for more that is allows for somewhat more efficient factoring than the algorithm proposed by Regev. So based on our new heuristic assumption, we can argue that we can find a basis for a lattice defined like this when A1 to AD are small primes. And with a basis for this lattice, we can actually factor the integer, target integer, in a somewhat different way to how Regev originally proposed his factoring. And this actually gives a slight performance advantage over Regev's originally proposed factoring algorithm, because Regev's weaker assumption required him to use A1 to ADs to be squares, whereas we do not have to have squares and can therefore select these numbers to be of essentially half the bit length, somewhat decreasing the cost of multiplying these numbers together and somewhat resulting in a somewhat more efficient factoring algorithm. A separate contribution of our work is an analysis of the robustness of Regev's algorithm and of our extensions thereof to quantum computer errors. And this is an important question because quantum computers, at least as we currently envisage them, are inherently noisy systems and may sometimes fail to produce the expected output. For Shor's algorithm, this is only a minor issue because for Shor's algorithm, we only require a single good run of the quantum circuit, and we can therefore just repeat the circuit until it's successful. Meanwhile, for Regev's algorithm, we must run the quantum circuit essentially square root of n times. And if we require all of these runs to be successful, then we can only tolerate a very small failure probability. And requiring such a tiny failure probability from the quantum computer may be a quite restrictive requirement when you actually design these in practice. And it would therefore be preferable if we had somewhat more robust post-processing. And there's actually been two separate works addressing this issue. First, in our work, we have actually analyzed Regev's originally proposed post-processing and argued for its robustness. Separately, Regev and Venkatrathan have developed a method to distinguish between good and bad outputs from the quantum algorithm, allowing filtering out the bad outputs. Now, our analysis of the robustness of Regev's post-processing relies upon a new heuristic assumption. With this new heuristic assumption, we can argue that the post-processing can actually be made robust to an arbitrarily large constant percentage of errors from the quantum algorithm. This does, however, require us to use somewhat larger parameters for the quantum algorithm to increase the robustness of the post-processing, meaning that a somewhat more costly quantum algorithm has to be used if we want a more robust post-processing. Meanwhile, Regev and Venkatrathan's filtration method does not rely upon any new heuristic assumption, but it does require significantly larger parameters for the quantum algorithm and a significantly more costly quantum algorithm to achieve the same level of robustness. Note, however, that it's quite natural that our heuristic approach can achieve a better concrete efficiency than an approach which does not rely upon any heuristic assumptions. To actually test our robustness in practice, we have also developed a simulator for the quantum part of Regev's algorithm and our extensions thereof. And this simulator samples from the distribution that we expect to get from the quantum algorithm. And this sampling cannot, in general, be performed efficiently classically, but there are some special form problem instances where we can perform this sampling efficiently. And it is these special form problem instances that are the focus of our simulator. And for these special form problem instances, the robustness of the post-processing behaves as we expected, providing some motivation for our new heuristic assumption. This also allows us to actually test which parameters are actually needed in practice to achieve a certain level of robustness, which is detailed in these graphs in terms of the cost of the required circuit to achieve a certain number or a certain robustness to a certain percentage of failed outputs from the quantum algorithm. So in this first graph to the left, you can see that to increase the robustness, you must increase the per run cost of the quantum circuit somewhat. But as seen in the second graph, the overall cost of the algorithm increases faster because we assume that the same number of good runs are available to the post-processing. And if there is a larger failure percentage, we therefore must repeat the quantum circuit more times to receive the same number of good runs, good outputs. And as the increased robustness of the quantum algorithm requires using the post-processing requires using a more costly quantum algorithm, it is not directly clear which level of robustness is actually preferable in practice, but this at least gives us the option to target or allow for a more robust post-processing when we actually design a quantum computer. Now, I would also like to mention some follow-up work, which me and Martin also did regarding the actual cryptographic implications of these new quantum algorithms. And this is available on Archive. And for this, to consider the cryptographic implications, we have done a cost comparison between Regev's algorithm with the space-saving optimization of Regev to previous variants of Shor's algorithm. And this comparison has been done for the per run cost of the quantum circuit in a cost model that is somewhat biased in favor of Regev's algorithm. Now, even in this biased cost model, it turns out that Shor's algorithm still has the advantage for most of the problem instances that we consider, as indicated by these red items in the table. An exception to this is for some instances of the general discrete logarithm problem, where our extension of Regev's algorithm actually has a slight advantage over previous variants of Shor's algorithm in our biased cost metric. This is, however, not of that great cryptographic importance, because for cryptographic implications, one typically considers some special form versions of the discrete logarithm problem. And for these special form versions of the discrete logarithm problem, there are specific optimizations of Shor's algorithm, which are not applicable to our extension of Regev's algorithm, and which makes our extension of Regev's algorithm quite uncompetitive. Now, a large reason, or essentially the reason why Shor's algorithm, even though it does not has an asymptotic disadvantage, actually performs better for these concrete problem instances, is due to the many optimizations that are available for Shor's algorithm, which do not straightforwardly transfer to Regev's algorithm. Although there has been some optimizations already developed for Regev's algorithm, we believe it to be an interesting open question to develop further such optimization in order to make Regev's algorithm more competitive with the previous variants of Shor's algorithm in practice. We would also consider it very interesting with an optimization of Regev's algorithm that's specific for these special form discrete logarithm problem instances that are relevant for cryptography. Because without such an optimization, it seems hard for our extension of Regev's algorithm to actually be competitive for these types of problems. It would also be very interesting with an extension of the algorithm to solve discrete logarithm problems in elliptic curve groups. But this seems to be a very hard problem to solve, because the efficiency of Regev's algorithm crucially relies upon the fact that the A1 to ADs are small integers, and no such notion of smallness exists for elliptic curve groups. And although we can make an extension quite naturally to elliptic curve groups, it does not come with the efficiency gain. So it's quite uninteresting. And in summary, we have extended Regev's algorithm to allow it to be used to compute discrete logarithm. We have also provided some further variants of Regev's algorithm, in particular, one that allows for somewhat more efficient factoring. Finally, we have analyzed and argued for the robustness of the post-processing for Regev's algorithm and of our extensions thereof. Thanks for your attention.
Thank you, Sue. Any questions?
Hi there, thank you for the lovely talk. My understanding is that these multiple runs of the algorithm give you vectors in the lattice, and you have this heuristic that says eventually you get a basis of the lattice, somewhat, or?
Sort of correct, but what we get is actually vectors close to the dual of the lattice, and we have to make assumptions about the shortness of a basis for the lattice.
Okay.
So it's if the lattice behaves as a random lattice, then everything holds. So if things behave as random elements, everything holds. But
okay, I was wondering, as a sort of constant factor improvement, you know, you're looking for this vector of all zeros and then 1 and minus e. Is there a way of quantifying the probability that that vector exists in a sublattice you generate before you've finished all of these runs? Or
we will still need the same number of runs, basically, because without this number of runs, we will not be able to get basically any information about the primal lattice.
I see. Okay.
So it's, the number of runs is not really related to if the vector we're looking for is interesting or not.
I see.
For Regev's original factoring algorithm, he's only interested in a single vector, and he still needs the same number of runs.
I see. Okay, thank you. Oh, and if I may, one more question quickly. With this comparison where you have these large instances where Regev's possibly wins, at what level of the quantum stack is this at? Are you embedding into error correcting codes here, or is this counting multiplications? Or
this is just counting multiplications, so it's ignoring quite a lot of costs.
Okay,
and these costs should probably be higher for Regev's algorithm because it needs more memory, even though it's even with the space saving optimizations, it has within a constant vector, but it is it needs like 10 n bits, qubits, whereas Shor's requires less.
okay, thank you so much.
Thank you. Any more questions?
Thank you for the very interesting talk. I have a question about, like, if I understand well, so if for the number or the problem size is bigger, so we have more advantage from Shor's algorithm. So basically, I just want to know with the progress of quantum computing, quantum computers, so would there be still any advantage from, the Regev's algorithm or from your algorithm?
I couldn't quite catch the question.
Yeah, just the advantage of Regev's algorithm compares to the Shor's one, original one. With if we have a more powerful quantum computer, so what's the advantage of these two algorithms here?
So the comparison here is independent of how powerful the quantum computer is. It's dependent on the problem size instances. So for sufficiently large problem sizes, then Regev's algorithm does have an advantage because it asymptotically have an advantage. But when we consider these smaller instances, which are the ones that are cryptographically relevant, then Shor's still has the advantage.
Okay, so basically, yeah, we have a small problem size. Okay, we will have some advantage here. Is that correct?
I'm sorry, I can't hear you.
If the number is small, so we will have some advantage from your algorithm here.
I can't hear you. I'm sorry.
Oh, okay. So if the problem, the number, okay, is small, the problem size is small. So basically, we can have some advantage from the Regev's algorithm and your algorithm. Is that correct?
If you mean the numbers in the table here?
Yeah.
So so they are the cost of Regev's algorithm divided by the cost of Shor's algorithm. So a smaller number means that our extension of Regev's algorithm is more efficient, while a larger number means that Shor's algorithm is more efficient for them.
Okay, so basically another question is like, if we, in the future, for example, if we have more powerful, like, quantum computer, so basically, is that possible, like, this kind of algorithm, Regev's algorithm, can be combined together with like Shor's algorithm, or just for the near term, application? Yeah, because like, well, maybe I missed something. If the problem size is bigger and bigger, so basically, the Shor's algorithm is always better, right?
Shor's algorithm is not always better. So when you get to sufficiently big problem instances, then Regev's algorithm is better. So if you consider, we have some breakpoints in the paper in this paper as well, where if you consider like 16,000 bit instances, then Regev's algorithm actually is better in this biased cost model. So if the progress, if we do not switch to post-quantum and instead just use larger and larger instances of RSA, then eventually Regev's algorithm will have the advantage. But this does not seem like the way the world works.
For the time, because we have limited time, and if you have any more questions, please take an offline discussion with Sue and Martin. Let's thank the speakers again and